Okay, so in this short video, I will explain about uh, time to failure. Okay, because to be able to calculate reliability, okay, we need first define what is time to failure. So the understanding of time to failure, okay, and its probability density function is important, okay, because that provide the fundamentals for our reliability equations. We will look into that later, uh, but first we need to look at what is the time to failure. Okay. Uh, so uh, we live nowadays. We live with things. Okay. With material. So with machine, with tools. Okay. So all these things. Okay. For example, car. For example, your car. Okay. uh, for example, your car. Okay. uh, at some point, okay, at some point it will fail. It fails. Okay. Failure of the your car could be due to many reasons. Okay. uh, it could be due to aging. Okay, aging. Okay. Mostly due to the aging. Okay, or wear and tear. Okay, because you use it, so you should expect that it will fail. It will fail, right? uh, so as the more you use, okay, or the older the car, or the higher the mileage of the car, okay, you should expect that the likelihood to failure will increase. Okay. So the question here is, the question that we want to ask, so the fundamental question we want to ask here: when will it fail? Okay. Or if is it in 1 year? Okay. 2 years? Okay. Maybe 10 years, so on and so on. Or if you consider, if you're not considering calendar time, okay, it could be, you could also consider the mileage. Okay, like maybe 100,000 kilometer, 200,000 kilometer. Okay, it fails. Okay, so the time to failure, it could be, you can use time calendar. Okay, like what in this example, I given as year as the time to failure. Okay, it could be months or hour. Okay, so on and so on. Okay, or like in the example of your car. Okay, other than the time calendar, it could be mileage of the car. Okay, so distance. So the distance travel also could be considered as the time to failure. Okay, or if you are not, if you are considering other things, okay, like maybe like bearing, okay, like bearing. Okay, this is my attempt to draw a bearing. Okay, so it could be the number of rotation. So so it doesn't necessarily has to be calendar time. Okay, it could also be other quantity. Okay. So next for example, okay, I will discuss about the time to failure, okay, using calendar time. Okay, so let's say, so the good example is CCTV. Okay. Let's say you bought a CCTV. Okay. This is timeline T, and here here you bought the CCTV. Okay. So and after that it is put into operation. Okay. So so the question we are asking now, okay, will it fail here or here, or when exactly it will fail? Okay, so uh, statistically, okay, we so because the time to failure, okay, is a random variable. Okay, it is not an exact value. Okay, you it could be that your neighbor CCTV functioning longer than yours. Okay, so so it is randomly distributed. So time to failure is a random variable. Okay, so we have to treat the time to failure as a random variable. Okay, and so so the time to failure could be small, it could be short, or long, or in the middle. Okay. So whatever it is, we don't know. So the best way to express time to failure is by treat it as a random variable. Okay, so so in statistics, okay, random variable is expressed using a probability density function. Okay, so let's let's let the y-axis is the likelihood, okay, or the probability, and the x-axis is t. Okay, so for the sake of this example, okay, let's say it's the distribution of the time to failure is let's say it's normal distribution. So we draw the normal distribution. Okay, so so is it, so if your CCTV behave as the a normal distribution, okay, so let's say this is T1, this is T2, this there is T3, okay, this is T1, this is T2, that is T3, okay, So the likelihood of that your CCTV fail at T1 is that, okay, or T2 is that, okay, and T3 is with that likelihood, okay. So next, okay, next if we if we ask if I say if I randomly ask what is the probability that it fails at T3, okay, so it is, okay, from this distribution, okay, so it is the, I'm drawing the curve again, okay, this is ft, this is t, okay, t1, t2 and t3. So if I ask what is the probability that it fails at t3, so it is equivalent to the area under under the curve, okay, that is shadowed, okay. So meaning that, okay, probability it fails at T3, okay, if you ask yourself, okay, the probability why it is the area under the curve, okay, it is because fails at T1 is also meaning that it fails at T3, okay, and failing at T2 also meaning that if you wait until T3, okay, the failure is already occurred, okay, which is why failure probability is the shaded is equivalent to the shaded area, okay. And an important consideration for this phenomena is that the failure occurs if the time to failure is less or equal than the T3, okay. So the question here is what is the probability that it fails at T3, okay. So it is it occurs if the time to failure is less than T3, okay. This is another way to explain that why the probability of failure at T3 is equivalent to the shaded area under the curve, okay. So this inequality, okay, shows that the T3 is what we want we want to know, okay. This is what we ask okay. Would it fail at T3, okay. This is what we ask, okay. And time to failure, okay, time failure is the character of time to failure is the character of our CCTV. So okay, so time to failure is the character, the CCTV, okay, which is random, which is random which is a random variable. Okay. Which is a random variable. Okay. And I just now I denoted it as FT. Okay. So mathematically, the probability of failure at time t, okay, and if you in a statistic, okay, the area, okay, the shaded area is actually the cumulative distribution function, okay, or we use the capital F, okay. So probability of failure is the probability that the time to failure is less, okay, or equal to the time that we ask, okay, whether it will fail or not, okay. In this example I use T3, okay, but for generality, okay, we don't have to put the subscript there. Yeah, I want to erase the subscript 3. Okay, which is okay, which is according to the probability, okay. So it is from 0 to 3, the probability density function dt. Okay. And if we back to our question just now, what is the probability that it fails at t3, okay, then what you have to do, okay, you put the subscript, okay, then you find your probability. Probability of failure at T3. Okay. Okay, and don't forget T must be T must be greater than 0. Okay. Because we are talking about, okay, the moment it is put into operation, okay, so the time must be greater than 0. And now that, okay, now that we know the distribution function, the cumulative, sorry my hands, I'm very sorry about my handwriting, okay. So since we know the cumulative distribution function, we can calculate the probability density function. Okay, so mathematically, okay, I will rewrite. I'm rewriting this equation, okay, the general equation. So ft equal probability of failure at time t is the probability that the time to failure is less or equal to the time that we are asking its failure probability, okay, which is 0 to t, and f, I don't want to use t inside here, okay, I will use u, okay, to make the equation mathematically correct, okay, du, but u is the argument, the argument u is still referring to the time, okay, time to failure. So so mathematically ft, okay, so ft, okay, f is, so you want, if you want to find f, okay, from this relationship, what you need to do is you need to differentiate, okay, both sides with respect to t, okay, so f equal to d over dt f t, okay, and I will continue to the next page, okay, so f t is the differentiation of f t with respect to t, okay, which is equivalent to the limit of delta t towards 0, okay, so dft, okay, so dft is d is f t plus delta t minus f t, okay, and delta t is t plus delta t minus t, okay, which is, if I rewrite that again, so it would be f t plus t minus f t over delta t, okay, and here is if you look in, okay, let's change the color. I want to change the color, make it blue, okay, so this term, okay, this term is the failure sorry about that, failure probability at t plus dt, okay, this term, okay, is the failure at t, okay, so f t delta t plus delta t minus f t is the probability that the probability of failure, okay, in or within, okay, within delta t. Okay. So it survived. It survived up to the so the CCTV still, this is important point, still functioning at time t, but in the next, but after that, okay, in the next delta t, it fails. Okay, so that's the meaning of this what should I say, that's the meaning of f t plus delta t minus ft. Okay, so change the color back to red. So it is equal to 0 probability that it's still functioning. Okay, it's still functioning at time t. Okay, so meaning that the time to failure, okay, is greater than the time that we are asking whether it fails or not. Okay, but it fails after it failed within delta t. Okay, okay. So let me show you my, let's use the laser. Okay, so this the numerator, okay, has the meaning that the probability of failure within delta t, okay, given that it's still functioning up to time t. Okay, so from time 0 to time t, the CCTV is still functioning, but in the interval of after that in the interval of delta t, it fails. Okay, so meaning that the time to failure is greater than the time that we are asking whether it fails or not. Okay, which is t. Okay, but less, the time to failure is less than the time that we are asking whether it fails in t plus delta t. Okay, and if so since delta t, we cannot, so delta t is not zero but small. Okay, the time interval we are considering here, it cannot be zero but small enough. Okay, so that we can approximate ft, okay, nearly equal to probability that it functioning until time t but fails after delta t. Okay, or simply the probability that it survive up to time t but fails in the next delta t, okay, nearly equal to the probability density function multiplied with the delta t. Okay, so okay, so if you know, okay, from the PDF of the time to failure of the CCTV, okay, and you want to ask, okay, let's say let's say since you bought the CCTV, it's now been 5 years, okay, so T is 5 years, okay, so you wonder uh, what is the likelihood that the CCTV fails after the next 1 year, okay. So the probability is the PDF, okay, multiply with 1 year, okay. That provide you the way to predict the likelihood that your CCTV fails in the next year, okay. Okay, you provided that you know the density function, probability density function of the time to failure of the CCTV. Okay, so now that we know now that we know we know how to find FT and FT and the density function and the probability or the cumulative distribution function. We can next derive the we can next deduce the formula for reliability, okay, and then failure rate function, okay, and then a few other parameter that I don't remember right now, but I will explain it in the next video, okay. So thanks for watching. If you have question, please leave it in the comment under. Thank you.